Hey everyone, welcome back to Abstract Algebra 1. This will be lecture 17 of this course, and in this section we're going to discuss polynomials, and specifically polynomials from the context of rings, of polynomials that happen to be rings. So they're obviously a mathematical concept that we're all very familiar with. If you're seriously taking this course, you've obviously encountered polynomials many times. And so we're going to be looking at them specifically with regard to how they exist as a ring. And then in the next section, we'll spend a little more time with polynomials, digging into factorization of polynomials. So we'll start with just kind of more basic notions of polynomials in the context of rings. So let's go ahead and get started on it. We'll call this section 3.5 Polynomial Rings. And so let's define a polynomial. We've certainly seen definitions of polynomials, but let's define a polynomial from the standpoint of being a ring. So definition, let's let R be a commutative ring. So let R be a commutative ring. Okay. Then the set of formal symbols. Okay, so what we're going to write is this: R of x, right? This is going to be equal to the set of an x to the n plus an minus 1 to the xn minus 1 plus dot 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 plus a1x plus a0, such that, of course, ai is in the ring R. Okay. And this is going to be called the ring of polynomials. So this is called the ring of polynomials. Okay, over R. Okay. And we would also say in the variable x. Okay, so if R is a commutative ring, it could be anything. I mean, I think we'll frequently just think of it as the integers. The set of formal symbols, anx to the n, dot dot dot, a1x, a0, such that the coefficients are all in whatever ring you're talking about. So when that's the case, the polynomials themselves happen to be a ring. Okay, and so just kind of reviewing some of the basic concepts of polynomials, but with an eye towards thinking about it from ring theory. So we would say two elements, and we'll say a of x, b of x in this ring of polynomials are equal if and only if for, let's see, a of x equal to, we'll say an x to the n plus dot 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 plus a1x plus a0, and b of x equal to b sub m x to the m plus dot 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 plus b1x plus b0. So these two polynomials from this ring would be equal if and only if ai equals bi for all I. Okay, right? So obviously the coefficients have to be equivalent, right? So the coefficient on the nth term has to be equal in both polynomials in order for the polynomials to be identical. Okay, now one of the things that's very important to wrap your mind around is the idea that really the x's here, the quote-unquote variables in the polynomials, they are less important from the standpoint of abstract algebra than they would have been in whatever other course you have seen polynomials, right? So it's not that they're less important, they just have a different function. Right, so in this definition, the symbols x, x squared, dot dot dot, x to the n, So x squared, dot, 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 x to the n. They don't really, we don't, their primary role is not that of variables. So are not primarily regarded as variables, or unknowns, however you want to think about it or articulate it, right? But instead we think of them more as placeholders that separate the ring elements. Okay, so x, the variables x that you see in these polynomials are not primarily regarded as variables, but instead as placeholders to separate the ring elements. Right, I mean, really you could just as easily well, not as easily, it would be equivalent to just treating them as arrays. You could write them as arrays or n-tuples, however you want to think of it. So for example, 2x squared plus 3x plus 5 could be written as 5, 3, 2, 0, 0, dot, dot, dot. Right? This would be another way to write it, and would preserve all of the kind of meaning that we need from the ring theory point of view, right? So 5 being the variable that is on the x to the 0, 3 being the coefficient on the x to the 1 variable, 2 being the coefficient on the x squared term, right? So it's really just placeholders. Here's the 0 position, the 1 position, the 2 position, so 0, 1, 2, right, and so on. So you could kind of think of it like that. The advantage with using polynomials is, I mean, it's somewhat more compact than having to write it like this, I think. But also the convenience, right? There's a convenience here when it comes to polynomials, because we're all really comfortable, usually by this point in your mathematical career, you're probably pretty comfortable manipulating polynomials. So the real advantage of using polynomials versus n-tuples is the ease of manipulation. Right, the ease of manipulation. I mean, there are some times when it is more convenient to actually have the variables written in there, but it's really like the ease of manipulation and just the general level of comfort that people tend to have with polynomials by this stage of the game. Okay, so we've set up above that we have this ring of polynomials. Let's talk about the operations on this ring. So what are the operations on Rx that make it a ring? Right, well, I mean, you're probably familiar with both of these things, right? So there's addition, polynomial addition, and polynomial multiplication. Right, so we've seen both of these. Let's talk about it in more rigorous terms than we probably have in the past. So let's let f of x equal a(n) x to the n plus dot 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 plus a1x plus a0, and g of x equal bm x to the m plus dot 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 plus b1x plus b0. Okay, so if m is greater than n, we can do the following. Right, so you've got to think about, so sometimes when we write these as polynomials, we typically will drop any terms where the coefficient is 0, right? And so in that case, in the case of m being greater than n, that would mean that there are terms larger than x to the n where the coefficients of g are not 0, right? But what we can do is we can kind of blow f up to match g. So if m is greater than n, we can write f of x equals a to the m x to the m plus dot 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 plus a to the n plus 1 x to the n plus 1 plus a to the n x to the n plus dot 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 plus a1x plus a0, right? And so what have I done here? Well, really just all of these terms. So a to the m, a sub m equals a sub m minus 1 equals dot 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 equals a sub n plus 1, which would all equal 0, right? But I can write them still in the as part of the polynomial if I like. Okay. Right, and so if I think about it like this, it's possible to add two polynomials term by term, even if they don't have the same degree, right? So it's possible to add f and g term by term, even if the degree of g is greater than the degree of f, as we've kind of stipulated here, if m is greater than n. Right, and so what that means is then that, so we would say f of x plus g of x is just a sub m plus b sub m x to the m plus dot 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 plus a sub 1 plus b sub 1 x plus a sub 0 plus b sub 0. Right? Now, all this means is that in the case of m being larger than n, this guy here just happens to be 0. That's okay though, right? It's still just 0 plus whatever b of m happens to be. Okay? All right, so addition just works. You can think of it as component-wise, basically. Kind of the same if you were to think of this as ordered pairs, you know, where you had an a of m, am minus 1, dot, 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 a1, a0, and you wanted to add to that all of the b's. You'd do the same thing, wouldn't you? Right? Component-wise addition on an m tuple like this would just be a sub m plus b sub m. And then a sub m minus 1 plus b sub m minus 1, and so on. So it's really the same idea. I mean, you could think it's really the same idea. So when we say that these things function as placeholders, we really do kind of mean it, right? Especially from the standpoint of the ring operations anyways. Now, addition is straightforward. We've all seen this. This is not a problem. Multiplication is somewhat more complex. So, I mean, it can be. Multiplication is more complex just because it's more tedious as an operation. But we would say f of x times g of x is equal to c sub m plus n x to the m plus n plus c sub m plus n minus 1 to the x times x to the m plus n minus 1 plus dot 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 plus c1x plus c0. Now, what the heck are all these c's? Well, where c sub k denotes this linear combination here, a to the c sub k denotes a sub k times b0 plus a sub k minus 1 b1 plus, and I'll write a couple more out, a sub k minus 2 b2 plus dot 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 plus a sub 1 b to the k minus 1 plus a sub 0 times b to the k. Now, what's happening here? Well, you're basically taking you know, if you're looking at the kth coefficient of the product, then it's going to be all of the combinations starting with a sub k and b sub 0 and decrementing the a subscript and incrementing the b subscript until you get to the other end. Okay, and this is going to be for k equal to 0, 1, ... up to what? M plus n, right? And so I know this may seem kind of foreign, but this is really just the familiar process of using FOIL and distribution of polynomials. So this is really just a more formal way of thinking about, you know, the good old FOIL method, and just distribution, right? Of, you know, when you're multiplying polynomials together, you do this already. It's just that this is a very formal way of kind of writing it out. Okay. All right. So let's do an example. Let's do an example here of how these operations thought of in this way work. So let's let f of x equal 2x cubed plus x squared plus 2x plus 2, and let g of x equal 2x squared plus 2x plus 1. Right, and so let's say, just to make things more interesting, let f and g be in z3x. Okay, so what does that mean? Well, z3x is the ring of polynomials over z3, right? So remember, z3 are the integers mod 3. So z3 is the integers mod 3. So that means what we have to do here is whenever, like if we were to add 2x squared and x squared, we would get 3x squared, but 3x squared is 0 mod 3. So we'd have to basically, you know, look at the least residue for all of the coefficients at all times whenever we're combining these things. So it just adds a wrinkle of like somewhat more interesting element to it. Okay, so let's kind of write this out. We'll just go through the whole process of adding these things together. So let's note that m plus n in this case is 3 plus 2, right? So f is m. We'll say m is 3 from the f polynomial, and n is 2 from the g polynomial. So m plus n is equal to 5. So that means we'll need an a5, an a4, an a3, an a2, an a1, and an a0. And we'll need a b5, b4, b3, b2, b1, b0, right? Okay, and so what are these things? So a5 is 0, a4 is 0, a3 is 2, a2 is 1, a1 is 2, and a0 is 2. So again, just pulling these off of here. So a2 is 2, a1 is 2, a2 is 1, a3 is 2, and then there's no non-zero terms above that. And so for b, it would be 0, 0, 0, and then 2, 2, 1, 2, 2, and 1. Right? So 2, 2, 1, everything else is 0. Okay. Right, so I know this is kind of the long way around, but we're just going to work this example end to end so you can see, get an exhaustive sense for how these work. And then let's add them together. So f of x plus g of x would equal, and I'm going to write it out, you know, in symbols first, just so we can be clear, a3 plus b3 x cubed plus a2 plus b2 x squared plus a1 plus b1 x plus a0 plus b0. And then, of course, this is just 2 plus 0 x cubed plus 1 plus 2 x squared plus 2 plus 2x plus 2 plus 1. And so this is 2x cubed plus 3x squared plus 4x plus 3. Now, remember, we're in the ring Z3, so we have to notice that this is actually 2x cubed plus 0x squared plus 1x plus 0 when we take mod 3, in mod 3, right? So these two polynomials would add together to give you 2x cubed plus x mod 3. Okay. So, I mean, it's real similar to what you're used to, but, you know, in this case, it's a little, you just have to be a little bit more careful. You know, this is the kind of thing you could easily program a computer to do, right? You plug in two polynomials, you could easily parse them out, add the coefficients, and, you know, calculate least residue really quickly, right? What about, and it's not necessary for addition, that's super simple, but with multiplication, you'll see it's quite a bit more involved. And these are even relatively small polynomials. So if I were to multiply these together, I would have I need c5 x to the fifth plus c4 x to the fourth plus c3 x cubed plus c2 x squared plus c1 x plus c0. I need all of those pieces, right? And so for each of these, we won't write them all out, but let's write out c5, for example. c5, remember, is going to be a to the fifth, b to the 0, a sub 5 b0 plus a sub 4 b1 plus a sub 3 b2 plus a sub 2 b1 plus, or sorry, b3 plus a sub 3, or a sub 1 b4 plus a sub 0 b5, and that's the coefficient for the x to the fifth piece. Okay, and then we'd go to the next. Now the good news is these get smaller as you progress through the polynomial, thankfully, otherwise it'd be ridiculous. It's already a little ridiculous, but the next term would be have as a coefficient a sub 4 b0 plus a sub 3 b1 plus a sub 2 b2 plus a sub 1 b3 plus a sub 4 a sub 0 b4, and that would be the x to the fourth plus dot dot dot, and we'll just kind of wrap it up here. And then the last term would be a sub 0 b sub 0, right? Because obviously these are all, I mean, we always start with b sub 0, and this will be a5, a4, a3, a2, a0, right? So eventually on the constant term, you're really just multiplying a0 and b0 together. All right. And then what you'd have to do is secondarily come in and just add all these numbers here. So it'd be like 0 times 1 plus 0 times 2 plus 2 times 2 plus 1 times 0 plus 2 times 0 plus 2 times 0. That's the x to the fifth term. Plus, I won't write these all out, but just give you something to look at to make sure you know how to plug these in. 2 times 2, 0 times 1 plus 2 times 2 plus 1 times 2 plus 2 times 0 plus 2 times 0. That's the x to the fourth term plus dot 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 plus 2 times 1. Now when you get all of this done, obviously this would be a very tedious process, you would get x to the fifth plus 0x to the fourth plus 2x cubed plus 0x squared plus 0x plus 2, and this would all be done in mod 3, right? So that's where you get a lot of these zeros. Okay, so there you go. So that's how that's how the two operations would work in the ring of polynomials. And I think it's clear, you know, when you look at how we've defined these, that these operations are going to be commutative, and they're obviously going to be associative, right? And so given all of this, it's fairly easy. It would be fairly easy to show that R of X is a ring. And I'll leave that to you. Right, you just go back to the definition of how do I show that something's a ring. Well, and then just do it. So it might be tedious, some of the operations, but I don't think it's too big of a deal. Okay. Very often, so again, the focus here isn't the polynomials, it's really the ringness of the polynomials. So very often what we'll find when we're looking at rings of polynomials is that depending on what the ring R is, certain properties from R will carry over to the polynomials over R. So very often we will see that the properties of R will carry over to the polynomials over R. Okay. And so here's an example. So if D is an integral domain, then the ring of polynomials over D is an integral domain. Okay, so D being that collection of numbers that we're going to use as the coefficients on our polynomials, if that collection of numbers happens to be an integral domain, meaning a commutative ring with no zero divisors, with unity and no zero divisors, then the ring of polynomials will be the same. It'll have the same properties. So let's prove this. And so commutative, well, I mean, clearly d of x is commutative if d is, right? Because all we're ever doing is dealing with the coefficients, right? So if I can commute the coefficients in D, if I can commute those numbers and along those operations, then I can do the same thing in the polynomial. That's not a problem. Secondarily, the unity question, if 1, so D is an integral domain, so it has unity. If 1 is the unity in D, then f of x equal to 1 is the unity element in the polynomial ring, right? And I mean, this is super easy to see. We'll just kind of quickly, like if you take any polynomial, you multiply it times the polynomial 1, then we know that that's just equal to a sub n x to the n plus dot 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 plus a sub 1x plus a 0. And then, I mean, really the only thing you have here is a b0, so you just have 1, right? And so all of the coefficients here would just get multiplied by 1, so it's 1 times a sub n x to the n plus dot 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 plus 1 times a sub 1x plus 1 times a 0. And so of course 1 times a sub n, right? 1 is the unity in D, so this just is a sub n x to the n plus dot 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 plus a sub 1x plus a sub 0, right? And so this is of course a of x, and so of course d sub x has a unity, and it's just f of x equal 1, the polynomial, the constant polynomial equal to 1. And then the zero divisor question. So how would we show that there are no zero divisors in d of x? So let's let f of x equal a sub n x to the n plus dot 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 plus a sub 0, and let g of x equal b sub m x to the m plus dot 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 plus b sub 0. Okay, and so remember, in the zero divisor definition, the two numbers being multiplied together cannot be 0, right? And so what that means here is that we have to specify that these polynomials are non-zero. So we'll say where a sub n is not equal to 0 and b sub m is not equal to 0 as well. Okay. And so what's going to happen when I multiply these together? Let's say, so we would say by definition, f of x and g of x has a leading coefficient a sub n, b sub m, right? That's gonna, that by definition, that will be the leading coefficient. Now, because D is an integral domain, right? D is an integral domain. Because D is an integral domain, a sub n, b sub m is not equal to 0 unless a sub n equals 0 or b sub m equals 0, right? And so that's going to extend to the polynomials. So f of x, g of x is not equal to 0 unless f of x equals 0 or g of x equals 0, right? Because of this leading coefficient, right? It picks it up there. That leading coefficient, when we assume that they're non-zero, it forces the whole polynomial to be non-zero, right? So that's how that works. Okay, so that's just an example of how the ring property gets extended and picked up by the polynomial over the ring. Okay. Okay, so we've talked about addition and we've talked about multiplication, the two operations for a ring, and the two operations that we're very familiar with when it comes to polynomials. Let's talk about the division for a moment, and we'll extend our discussion to be polynomials over fields for this section. So we've used the division algorithm repeatedly with integers. We're very familiar with it, the division algorithm. Okay, so if a and b are integers with b not equal to 0, then we say there exists a unique, well, there exists, sorry, not a unique, there exists a q and r integers such that, what? Well, such that we can write a equals b times q plus r, right? Where 0 is less than or equal to r, which is less than b, and we'll say absolute value of b just to be careful there. Right, and so this is something we're very familiar with. We've used this a lot. This is the division algorithm. Right, and so the next theorem that we'll talk through is basically the analogous statement, but for polynomials over a field. Right, so the next theorem is analogous, but for polynomials over a field. Okay, and so what is a field? Remember, a field is just a ring, but with every element being a unit, right? So it's a ring with unity, and in addition to that, every element is a unit, meaning all of the elements in the field have multiplicative inverses. Okay, so the integers are not a field, right? They're not a field. They're a ring, but they do not have multiplicative inverses for all of the elements. Okay, so this is how the theorem goes. Okay, and this would be the division algorithm for polynomials. So let's let f be a field and let f of x and g of x be in the field of polynomials over f, right? And we'll say with g of x not equal to 0, so not equal to the 0 polynomial. Okay, so then there exists a unique q of x and r of x in f of x the field of polynomials over F, such that, right, so very similar to the definition for the division algorithm over the integers, but now we're talking polynomials over F, such that f of x equals g of x times q of x plus r of x. Okay, and either we'll say if g divides f, then r of x equals 0, or in the case where there's a remainder, we say that the degree of r is less than the degree of g. Okay, so same conditions really as up here. Here we say r is greater than or equal to 0 in the case of strict divisibility. But if there is a remainder, it must obviously be less than b. And so we're saying the same thing here. The remainder has to have degree less than whatever g's degree is. Okay. And so just like in the division algorithm for integers, we say that the polynomials q and r would be the quotient and the remainder. So we say q is the quotient and r is the remainder. Okay. Now, when the ring of coefficients of a polynomial ring is a field like this, then we can use the long division process to determine the quotient and the remainder. Right, so remember, this doesn't work necessarily in a polynomial ring, right? Because division isn't guaranteed to actually work, right? But let's see an example, and we've certainly seen this before. But let's take a look at an example. Let's divide 3x to the fourth plus x plus 1 by 2x squared plus 2. Okay, so what would we do here? We would say, all right, 3x to the fourth plus 0x cubed plus 0x squared plus x plus 1. And there's slightly different conventions depending on where you've seen this in the past as far as how you set this up and how this works. But we would say that 2x squared plus 2 goes into this. And we would start by saying 3/2 x squared. Remember, we need to, what we're trying to do is when multiplying this term by this front term, we want it to equal this, and so that's hence the 3/2. So 3/2 x squared times 2x squared is 3x to the fourth. Okay, so that's that one plus, and then we have to multiply this times this, so that would be 3x squared, and so it'd be plus 0x cubed plus 3x squared. And then we would do the subtraction here. Okay, so 3x to the fourth minus 3x to the fourth is 0, and then you got a 0 there, and then 0 minus, this would be minus 3x squared, and then you could bring the polynomial down, right? Bring the other terms down. Okay, so this is how you would proceed, right? So let's see, f of x would be equal to g of x, q of x plus r of x, and in this case, what would all of these quantities be? All right, so this would be, we would say the f of x is 3x squared, 3x to the fourth plus x plus 1, right? That's this thing in here. That's going to be equal to the g of x, which is 2x squared plus 2. 2x squared plus 2. And then we would say the q of x is the 3/2 x squared. And then the remainder would be plus this thing. Okay. All right. So that's the idea, right? We can just run through this like this. Okay. Very good. Very good. So if D is an integral domain, then we say that for f and g in D, we say that g divides f if the remainder is 0. Okay, let's talk that through. Let's jump to that next. So if D is an integral domain, if D is an integral domain, then we say that for f and g in the polynomials over D, that g divides f if there exists some h of x in f of x. All right, there's going to have to exist some polynomial h such that f of x equals g of x plus, or times h of x. Okay. Right, so, I mean, basically the r of x is 0 in the division algorithm. And in this case, we would say that g of x is a factor of f of x. Right, we would say that g of x is a factor of f of x. Right, so just like what we would say the same thing if we were talking about just like integers, right? If we said 10 equals 5 times 2, then we would say, yes, 2 is a factor of 10. 5 is a factor of 10 also. Okay. Okay, now important to notice here we have an integral domain, so that implies that g and h can't be 0, right? Okay, what it implies is that if the product equals 0, then one of them is 0. Okay, it's an integral domain. Okay, so kind of we're headed towards something here, so we're kind of bringing up some things that we've seen in the past and trying to think them through a little more from the ring theory perspective. So what we also say that an element A is we've heard this term a million times, a 0 or a root of f of x if the polynomial evaluated at a is equal to 0. Right, so we've obviously heard of all of these things. So when f is a field, A is in f, and f of x is in the field of polynomials over f, we say that A is a 0 of multiplicity k. It's a 0 of multiplicity k, and this is going to be for k greater than or equal to 1, if x minus a to the k is a factor of f of x. Okay. This is similar to the repeated roots concept. It's the same concept, really. Right? So we say that A is a 0 of multiplicity k if x minus a to the k is a factor of f of x. And importantly, we would also have to say that x minus a to the k plus 1 is not a factor of x. Right, so it's the largest such factor. That's where the multiplicity piece comes in, right? Certainly if x minus a to the k plus 1 is a factor, then x minus a to the k is also a factor, but it's not a factor of multiplicity k. In that case, it would be a factor of multiplicity k plus 1. But if k is the largest such factor, the highest degree polynomial that's a factor of f, then this definition holds. Okay. All right, and so with these things in mind, we can jump to a string of corollaries related to the division algorithm for polynomials. So a string of like smaller theorems that are very closely related to the idea of the division algorithm for polynomials. So the first one, let's let f be a field. Okay, we'll say A is in f, and f of x is in the field of polynomials over f, then f of a is the remainder in the division of f of x by x minus a. Okay. So f of a is going to be the remainder in the division of f of x by x minus a. Okay. The second one, let's let f be a field. A is in f, and f of x is in the field of polynomials over f. Then a is a 0 of f of x. It's a 0 of f of x if and only if x minus a is a factor. Okay, and so these things can be proven very easily by just resorting to the division algorithm. Okay, and we won't prove these, but again, they, as I just said, they could be shown just using the division algorithm that we just talked through, right? And so some of the informal definitions for what do we mean by a remainder, what do we mean by a factor, etc. Okay, the last corollary we will prove, just because it's a super important one actually. So the last one says that a polynomial of degree n over a field has at most n zeros, counting multiplicity. Okay, so this is hitting very close to what we would think of as the fundamental theorem of algebra, which says essentially that the number of roots of an algebraic equation there are as many roots of an algebraic expression as there are as the highest degree of the polynomial. It's of a polynomial, right? It's a fundamental theorem of algebra. And this is very similar. This is a similar concept, but and we can prove this just using the ideas that we've talked through here. So let's go ahead and walk through this proof. This is a good one. It's challenging, but it's not mind-bendingly difficult by any means. Okay, so let's prove this one. Okay, and so what we're going to do when we prove this, we're going to actually use induction. So we'll use an induction argument on n, right? So n will be the degree of the polynomial, right? So we'll start with the base case where n is equal to 0. So letting n equal 0, we can obviously see that a polynomial of degree 0 has no roots. So a polynomial of degree 0 has 0 roots. Okay, got it. All right, so let's suppose then that f is a polynomial of degree n. It's a polynomial of degree n over a field, right? Over a field, and let's suppose that a is a 0 of f. Suppose that a is a 0 of f, and let's say that a has multiplicity k. Okay? And so what that means, given what we've just talked about, is that we could say then that f of x is equal to x minus a. So a being a 0 means that x minus a is a factor, and the fact that it has multiplicity k means that x minus a to the k power times q of x, whatever that happens to be, is equal to f of x. And further, we could say that q evaluated at a would not be 0. Okay. All right. Okay, so this is just the starting point, right? This is where we would start with. So we could say all of these things just based on the definitions that we've talked through and the couple of corollaries that we've looked at that we didn't prove, but I think probably people would be able to show them on their own. Now, what else do we have here? Well, what's the degree of f? The degree of f is n. Okay, and so that must be equal to the degree of this business, x minus a to the k times q of x. Okay, and so we know the degree of this, so the degree of x minus a to the k is obviously k, and so this must be equal to k plus whatever the degree of q is. Right, that's how that would work, right? The degrees would add, so whatever the highest exponent is here, you'd add to that, and that's how the degree would increase, right? Okay, and so we obviously know that k is less than n, so this would imply obviously that k is less than or possibly equal to n. I mean, q could be a constant. That's possible as well. Okay, all right, so this part's straightforward so far. Okay, where's the big hook come in? So let's say that if f has no zeros other than a, we're done. Right, if a has no zeros other than a, if f has no zeros other than a, then we're done. Right, so let's assume, right, let's assume, well, in that case, k would be equal to n. Right, this would be degree 0, right? And so let's assume on the other hand that, so we'll say on the other hand, if b is not equal to a and b is a 0, and b is a 0 of f of x, then what? Well, then 0 would be equal to f of b, right, which would be equal to b minus a to the k power times q of b. Right, so in this case, b would also be a 0 of q of x. Okay, so z would also be a 0 of q of x. So we know that q of x has at most, so the degree of q of x is equal to at most n minus k, right? Counting multiplicity. Right, and so that means that q of x has at most n minus k zeros. Okay, counting multiplicity. Okay, and so therefore, right, therefore f of x has at most k, right? So jumping back up to this piece, k plus, now we just said this is going to have at most n minus k zeros. So f of x has at most k plus n minus k equal to n zeros. All right. And so that's what we were out to show, right? That f of x has, if f of x is a polynomial of degree n, then it has at most n zeros. Okay. All right. So make sure that one makes sense to you. Go back through, fill in any things I left out. I think I might have skipped over a few things in the interest of time, but the essentials are there. The essential argument is there. Okay, and so we're going to conclude with just a brief introduction to the idea of a principal ideal domain. This will come up later in the course, or later in Algebra 2, actually. And so I want to define it now. It's convenient to define it now because it is to do with polynomials. At least a big piece of it is. So let's say that a principal ideal domain, okay, is an integral domain. Right, so integral domain, remember, commutative ring with unity, no zero divisor. So a principal ideal domain is an integral domain R in which every ideal has the form A equals R times A, such that R is a ring element for some A in R. Right, so every ideal in the ring is going to have this essential form. Now, note, ideals can have different forms in this. They don't have to be built in this way, but in a principal ideal domain, they all have this form. Okay. And so the theorem that we want to end on here is this. So let F be a field, then f of x, the field of polynomials over F, is a principal ideal domain. Okay, so if F is a field, then automatically the ring of polynomials, the field of polynomials over F is going to be a principal ideal domain. Okay, and so this one is actually really easy to show, and it's a nice proof to end on. So we know that f of x is an integral domain. Right, we know that f of x is an integral domain, right? Because f is a field, and so we have the property we need there. Let's let I be an ideal in f of x. Okay. Now, if I is equal to just the zero polynomial, then we could say that I is equal to 0, right? It formed in this way, right? So that's not a problem. Obviously, R times 0 is going to be a totally legit way to build up the ideal, right? So if, on the other hand, if I is not equal to just 0, then we would say among all the elements of I, let's let g of x be one of minimum degree. So let's let g of x be the element, let's let g of x be the element in I that is the smallest, has the smallest degree. There may be multiple elements that have the same degree that are small. Let g be one of them. Right, so for example, if we're talking polynomials here, if the smallest polynomial has degree 2, then g of x is a second degree polynomial. If the smallest polynomial in I is a constant, then g of x is a constant. Okay, and so what we're going to show then, we will show that our ideal is basically built up using g of x in the manner specified in the previous definition. Okay. All right. So how will we do this? Well, what we'll do is we'll start with the fact that g of x is in I. So since g of x is in the ideal, we have what? We have that all of the elements we can multiply against g of x must be in the ideal as well. Okay. Now let's let f of x be in I, right? It's in the ideal subring that we're talking about here. Now by the division algorithm, we have, well, f of x equals g of x times q of x plus r of x, right? We'll see about that, but plus r of x, where r of x is equal to 0, or the degree of r is less than the degree of g. Okay. All right, so what do we have here? So since f of x, since r of x, kind of reverse this, r of x is equal to f of x minus g of x q of x. Okay, what can we say here? Well, f of x is in I, g of x and q of x, well, g of x is in I, right? Right, and so this whole thing is in I, right? Okay, so since r of x equals f of x minus g of x q of x is all in I, the minimalness of the degree of g is going to imply that the latter condition can't hold, right? The minimality of the degree of g implies what? What did I just say? Well, it implies that the latter condition cannot hold, right? Namely, i.e. that the degree of r be less than the degree of g. Right, this piece here. And so if the degree of r can't be less than the degree of g, but we can still do the division algorithm because of the division algorithm, then the implication is that the r of x is equal to 0. Right, then r of x is equal to 0. And we would say f of x is in the ideal generated by g of x. Right? Since what? Since f of x equals g of x q of x. Right? And so this shows what we need, right? This gives us what we need. So this all implies that the ideal is a subset of, as a subring of the ideal generated by g of x, which is exactly what we needed. Right? So f is a principal ideal domain because we just took an arbitrary ideal in this field of polynomials in f and showed that it has to be built up in this way using this guy here, specifically using the idea of g of x equal to f of x g of x such that f of x is in r of x. Right? So this arbitrary ideal has to be built in this way. If G is the polynomial in the ideal with minimum degree, then it generates the whole ideal. Okay. All right. Very good. That's where we'll end it. Now the next lecture will actually be the last lecture of the course. And in that one, we're going to continue with polynomials. We're going to get into factorization of polynomials. So it's going to be very similar to this topic, just extended into, we're going to cover more of the concepts that you're familiar with regarding polynomials, but but from the standpoint of what is a ring, and the polynomials happen to be a ring, etc. Okay, so we'll leave it at that. And we will talk to you all next time. Take care.